Hello everyone, welcome back to the latest lecture session. We are discussing about lime soda softening. We now have enough background in the relevant aspects, so let's dig right in. In the last one, we were trying to look at removing CO2 first, the acid, if that's present, right? I'll have to remove that by adding lime, Ca2 plus and 2OH minus and the relevant products. And in the second one, I think we looked at removing calcium that is associated with carbonate hardness. Thus, there is already enough carbonate. What does it mean? I have Ca2 plus and I have some HCO3 minus, right? But I don't have enough CO3 2 minus, which I want, because the solid that will precipitate out is CaCO3, the solid. So if I add the Ca2 plus and OH minus will increase the pH and thus change HCO3 minus to CO3 2 minus, and thus CaCO3, the solid, will be precipitated out. In that manner, both the calcium that's initially present in the water and the calcium I am adding along with lime, this is lime, right? When I add lime, are being precipitated out. And the next one will be magnesium associated with carbonate hardness. So I have Mg2 plus in my solution, and I also have the relevant carbonate. And so if I am adding relevant lime, okay, I should have said 2OH minus here, plus 2OH minus, this is lime, and this is what is already in the water. So it will see to it that, assuming that enough or high enough pH has been raised, or the pH has been raised to the high enough value, magnesium hydroxide will precipitate out, and also conversion of this bicarbonate to carbonate will take place, and also CaCO3 will precipitate out, right? And the fourth one is magnesium due to non-carbonate hardness. So here I have magnesium associated with ions other than carbonates, right? So how do I remove them? Here I am adding Ca2 plus and OH minus, right? So I am increasing the pH by adding lime, and thus I will have magnesium hydroxide being removed, let's see, right? Or magnesium being removed in the form of magnesium hydroxide. But what about the calcium that I added here? So for that I will have to add a source of CO3 2 minus. What is the source of CO3 2 minus that we are adding? That's the soda ash, Na2CO3, right? So if I add that, I will then also have source of CO3 2 minus, and then the calcium that comes with lime will also be, I should not have written this, will also precipitate out, let's see, right? So this is because the magnesium is associated with non-carbonate hardness. And then what about the calcium that's associated with non-carbonate hardness? So same case, here I am going to add, I have calcium associated with other ions other than, anions other than carbonates or bicarbonates. So to remove this, I am adding the relevant soda ash, right? This is the soda ash, and then I am going to have relevant removal of solid. Again, these reactions are not balanced, but I am just looking at the relevant solids that are being formed. So what are we adding here at different stages? Here we are adding lime, right? Here we are adding lime. Here also we are adding lime, 1 mole of lime per 1 mole of calcium that's present, and here also for 1 mole of magnesium carbonate hardness present, I am adding 1 mole of lime, right? In the case of magnesium carbonate hardness, what is it that I seem to be doing? Anyway, if the stoichiometry doesn't add up, we will look at it and change it later. Okay, here I guess I will have to add 2. Yes, I guess so, because of the stoichiometry here, if I want CaCO3 to be formed. Again, maybe rather than looking at the unbalanced equation, it will be better to look at the balanced equation later. But here we are adding lime, here also lime, here also lime. In the case of magnesium non-carbonate hardness, I am adding both lime and soda ash. In the case of calcium non-carbonate hardness, I am adding soda ash, let's say, right? So soda ash obviously comes into picture when we are dealing with the non-carbonate hardness related aspect, right? That's something to keep in mind. Let's move on. So what is it we are adding? We are adding lime. This is from McKenzie et al. So, lime, we are adding it to neutralize CO2, right, neutralize H2CO3 or the dissolved CO2, and lime enough to alkalinity or HCO3 minus. Why? I want to raise the pH and convert HCO3 minus to CO3 2 minus, right. Then CaCO3 will precipitate out, and then lime equivalent to magnesium to be removed. Why? I want to raise the pH such that magnesium hydroxide precipitates out. And this we haven't mentioned earlier, but typically lime is required in excess, because just if it's stoichiometrically relevant, the reaction will not take place. You want it to be supersaturated. The solution has to be supersaturated for that precipitation reaction to be driven, right. For that, you are typically going to add an excess, let's say. This depends from one particular case to the other, right, but there are thumb rules in general. This is added to drive the reaction. For non-carbonate hardness, obviously what is it we want? We want CO3 2 minus source. So, soda ash or soda, because non-carbonate hardness has to be removed. So, we are providing CO3 2 minus, let's say. So, this is why we are adding it. In general, this is called lime addition, and this is called excess lime addition, let's say. When I am also adding lime to remove magnesium and such, I am going to refer to it as excess lime addition. And then obviously, if I am removing non-carbonate hardness, this is the soda ash, let's see. Again, this is a good overview. Let's see what else we have, and more importantly, stoichiometric ratios. Why? Well, whatever questions people ask are typically going to be based on stoichiometry, and depending on how well they think, they can look at the fundamental assumptions and change them around. So, let us look at the stoichiometric ratios and the relevant reactions, let's say, which I did not balance earlier. The first one should be with respect to the carbon dioxide, right. So, we have carbon dioxide and it is an acid. So, this carbon dioxide will typically be in equilibrium with H2CO3. If it is there, it has to be neutralized so that the pH can be raised, right. So, whatever lime that I add, I am assuming that it is initially going to be taken up by carbon dioxide, and I guess CaCO3 is going to precipitate out, right. S is for precipitate. Let us see if it is balanced. Ca and CO3 and H2O. So, looks like it is pretty well balanced, let us see. So, what is it? Stoichiometric ratio, right. I need to understand for how many moles of carbon dioxide present, how many moles of lime I need to add, and so on and so forth, right. Then I can easily calculate it. So, let us see that. So, for 1 mole of lime, right, you see here stoichiometric coefficient here is 1, has to be added for 1 mole of carbon dioxide, right. Here if we look at it with respect to charge, CaOH twice, right, it is either Ca2 plus 2 charge 2 equivalents, or 2 OH minus, right, 2 again charge equivalents. So, here it is 2 equivalents with respect to CaOH twice, and also CO2 I know is H2CO3 in solution. So, it is either 2H plus, again 2 charge or equivalents, or CO3 2 minus. So, 2 charge or 2 equivalents, let us say. So, it's equivalent to 2 equivalents per 2 equivalents, right. And then obviously, if it is equivalent per equivalent, if I want to convert it into units of CaCO3 and such, so it is 1 milligram of CaCO3 equivalent per milligram of CaCO3 equivalent, let us see, right. So, that is one thing to keep in mind, right. So, let us go further. Soda ash, do we add any carbonate here? No, right. So, soda ash, none required. Next aspect, the reaction is with respect to removal of calcium associated with carbonate hardness. So, calcium that is associated with carbonate hardness. So, what are we adding? We are adding lime, and you can look at the stoichiometric ratios and such, but you see that 2 moles of CaCO3, the solid will precipitate out. Let us look at the ratios that are required. So, I am having to add 1 mole of calcium hydroxide per mole of calcium, let us say, that is associated with carbonate hardness. 1 mole of calcium hydroxide per 1 mole of calcium carbonate, not calcium associated with carbonate hardness. So, 2 equivalents per 2 equivalents, right, that is something to keep in mind. 1 milligram per lime as CaCO3 per milligram of CaCH expressed as CaCO3, but once we get it in terms of equivalents, it is pretty easy obviously, right. Let us move on. So, we are done with calcium carbonate hardness. We will look at magnesium. Is it okay? Am I adding any soda ash here? Is any HCO3 or CO3 2 minus required? No. Why is that? Because already we are dealing with the carbonate hardness part, and we are assuming that, not assuming. So thus there is enough bicarbonate or carbonate present. We just need to increase the pH, right? What are we doing in this reaction? We are adding lime and increasing the pH, right? So next one, magnesium associated with the carbonates, let's see. So what is the reaction here? I have magnesium associated with the carbonates, and here I know that magnesium will precipitate as magnesium hydroxide. Yes, so I want to increase the pH by adding lime. So that's why we have magnesium hydroxide being precipitated out. But why am I adding 2 moles? Right, because here my role is not just to remove the magnesium that's present, I also want to remove the what is this? Calcium that I am adding here. So if I add it here again, you see that I have to increase the pH such that HCO3 minus in the solution will, what do we say, be transformed into CO3 2 minus. So for that I also need to add enough OH minus, and then the calcium will be precipitated out as CaCO3, right? So for that I am adding 2 moles, let's say. Am I adding any soda ash? None here. So take home message is, for 1 mole of magnesium, 2 moles of calcium hydroxide will be added. So stoichiometric ratios, what we just mentioned, 2 moles of calcium hydroxide per 1 mole of magnesium associated with carbonate hardness. So that's why it's 4 equivalents per 2 equivalents, meaning 2 milligrams per lime as CaCO3 per 1 milligram of magnesium associated with carbonates expressed as CaCO3, right? But again, why is this 2? You can see that one is for precipitating out magnesium hydroxide, the other is for transforming HCO3 minus to CO3 2 minus, let's say, right? That's why we have 2 moles here in this reaction. Are we adding any soda ash? None, right? Why? Because it's already carbonate hardness. We are assuming that there is already enough carbonate present there or bicarbonate present there. So what about the magnesium now that is associated with the non-carbonate hardness, right? So let's look at that. So here 2 aspects. Magnesium has to be precipitated out as magnesium hydroxide, so I need to add lime, right? Because I need source of OH minus to increase the pH. The second one is I also need to be able to remove the calcium. If not, that will add to the hardness. So to remove that calcium, I will also need to add a source of carbonate. Why? Here it's the one associated with non-carbonate hardness, meaning no more carbonates or bicarbonates present here. Just raising the pH is not good enough. So I will also have to add a source of carbonates, which is soda or soda ash, let's see. So let's look at that. Magnesium associated with other ions, non-carbonate hardness. So I'm adding lime and then the soda ash. So when I add lime, this OH minus, it will lead to increase in pH and precipitate out the relevant magnesium hydroxide. And what about this particular Na2CO3? What will that do? It will give the source of CO3 2 minus, so that calcium that comes in with lime is going to be precipitated out, right? So you can just understand the equations. So this Na plus is obviously out here, let's see, right? So this Na plus is obviously out here on this right hand side. So stoichiometric ratios, let's see. So for 1 mole of magnesium associated with non-carbonate hardness, I need to add 1 mole of calcium hydroxide. So 2 equivalent per 2 equivalent, right? And thus 1 milligram per lime as CaCO3 per 1 milligram of non-carbonate hardness, magnesium non-carbonate hardness expressed as CaCO3. But what about soda ash? Yes, I am adding 1 mole of soda ash per mole of magnesium. Same case here. So 1 mole of soda ash Na2CO3 is added per 1 mole of magnesium non-carbonate hardness. So it's again 2 equivalents. It should not be 1, I guess. It should have been 2. 2 equivalents with respect to magnesium non-carbonate hardness. So 1 milligram of soda ash as CaCO3 per milligram of non-carbonate hardness, magnesium non-carbonate hardness expressed as CaCO3, right? So again, one correction here, that's something to keep in mind. And let's move forth. So I'm done with removing calcium due to carbonate, magnesium due to carbonate and non-carbonate. So I'm still left with calcium due to non-carbonate hardness. So for that, obviously, what is the approach? There is no carbonate, so CaCO3 can't precipitate out. So I'll have to add CO3 2 minus. Why is it that we are looking at this at the end? Well, because two ways. One is we are adding lime to increase the pH. So only if I increase the pH and add the relevant soda ash, well, CO3 2 minus stay as CO3 2 minus. If not, if I keep the pH around 7 and then add Na2CO3, yes, pH will rise a bit, but not enough for the CO3 2 minus that I am adding in the form of Na2CO3 to stay as CO3 2 minus. It will instead maybe stay as HCO3 minus. So that's one reason here. So what is the reaction? Calcium, that's why we are looking at this part at the end, assuming that we have raised the pH high enough, whatever Na2CO3 that I add will see to it that the CO3 2 minus from here will stay as CO3 2 minus mostly. So we are adding soda ash because we want to add a source of CO3 2 minus, and that is precipitating it out, CaCO3 the solid, and we are done with it, right? Am I adding any lime? Not necessary here at this stage. So lime, none required. And what is it now? We have 1 mole of soda being added for 1 mole of calcium associated with the non-carbonate hardness. So 2 equivalent per 2 equivalents, and thus 1 milligram of soda ash expressed as CaCO3 per 1 milligram of calcium associated with non-carbonate hardness expressed as CaCO3, right? Again, typically note that we add units in terms of CaCO3. In general, if you are not able to remember, just understand that we are trying to remove CaCO3 solid and magnesium hydroxide solid, and then you can just try to see how much of soda ash or how much of your lime has to be added to be able to precipitate this out, and then you will get the relevant equivalents, right? So let's see if we can summarize that. Okay, another aspect, in general we have to add an excess dose. Why is that required? Because we want to keep the solution super saturated. Just saturation or adding the amount just stoichiometrically enough for triggering the relevant precipitation will not be good enough. That is why you need to add an excess dose to drive the relevant reaction. So here they are saying that it's from 20 to 40 milligram per liter expressed as CaCO3. This is with respect to lime, let's say. Lime expressed in the units of CaCO3, you need to add almost 20 to 40 milligram per liter. So here is a summary of what we looked at. If there are any errors, you can change that. When we, let's just go through that. When we are adding carbon dioxide meaning H2CO3. So there is already enough CO3 2 minus present there. So if I just add lime, it's going to precipitate out as CaCO3. That's why 1 mole of what is this? CaOH twice. Let me write it down, CaOH twice, right? So CaOH twice is lime, soda ash is Na2CO3, and let me write out here what's going to precipitate out. So here 1 mole of CaCO3 will precipitate out, right? So calcium due to carbonate hardness, again I am adding lime, CaOH twice. So 1 calcium is already here and 1 calcium is coming from here. So if I add 1 dose of CaOH twice, that should be enough to increase the pH such that HCO3 minus is converted to CO3 2 minus, pardon me, and then I am going to have precipitation of this, let's say, right? And then what about calcium non-carbonate hardness? Non-carbonate hardness, what do I need to add? I need a source of CO3 2 minus. So that's why I am adding soda ash and I am not adding any relevant lime. So what is it that will precipitate out? CaCO3, the relevant solid. What about magnesium, the carbonate hardness? Here we have 2 aspects for increasing pH. One is to precipitate out in the form of magnesium hydroxide. So that is why we already have one or requirement for 1 mole of lime. And why do we need the second mole of lime? Because we already have 1 calcium that's coming into the solution when we added lime for increasing the pH. So for precipitating out that lime, we will have to add this particular lime too, right? 2 CaCO3 solid. So you can understand why we are adding 2 moles. The one associated with magnesium non-carbonate hardness, what is it that we are doing? We are adding 1 mole of lime to increase the pH. So magnesium hydroxide, the solid, will precipitate out. And also to precipitate out the calcium that we are adding when we added lime here, we will have to add Na2CO3, right? So I am going to remove CaCO3, the solid. So right, this is what we have, and from that you can understand this, right? And what is the dose here, excess? Why am I adding this? To keep it super saturated. Typically I am going to add this excess dose expressed as CaCO3, right? So this is a summary of what we have looked at until now. That's something to keep in mind here. Let's move on. So, approach is, typically for hardness, yes, allocate hardness first to calcium carbonate hardness, then I guess look at calculation of calcium non-carbonate hardness. If there is alkalinity left, you will assign it to magnesium carbonate hardness, and depending on the amount of magnesium left, you will allocate it to magnesium non-carbonate hardness. So, from this you will also look at what is the removal required. So, here I have to mention this. Why am I not saying just that I need 0 milligram per liter? Well, two aspects. Well, if I have it this way, it's going to lead to corrosive water, right? You don't want it to have, what do we say, no precipitate being formed. Sometimes people want to form a thin layer of the CaCO3 in the pipe so that acts as a protective coating. It prevents the pipe from being corroded. Other than that, because these equations, as you can see, CaCO3, the solid will be in equilibrium with Ca2 plus and CO3 2 minus. And we saw that there was a equation for this, Ksp is equal to what, Ca2 plus into CO3 2 minus, and I think we saw this equation something to be around 10 power minus 9. We saw this in one of the earlier graphs in this session or the previous session, right? So, looks like I overshot that here. Okay, so we are back on track. So, as you can see, you are always going to have it in equilibrium. You will never be able to reach 0. So, to be able to reach very low values, you will have to keep adding more and more of this lime or the soda ash, which is not feasible. And more importantly, it's always at equilibrium. So, how much ever you remove, some calcium will always be in equilibrium with that particular solid, let's say, right? It's in equilibrium, right? So, if it's like this, you can maybe bring it down here, but you will still have equilibrium. So, you will always have some calcium. So, with this process, the way we are doing it, you can't get obviously 0 hardness, and also you would not want to have, what do we say, everything removed, because if this is the pipe, you want to have a thin, what do we say, coating, such that the pipe is not corroded. Otherwise, the water is deemed to be corrosive. I think we will look at this now. And then you allocate hardness to calcium carbonate hardness. I would then do it for magnesium carbonate, magnesium non-carbonate, and calcium non-carbonate hardness. But others would also say that you will have this here and in that order, but it does not make too much difference here, right? So, what is the approach? This is the aspect. First, calculate the hardness and associate and give it to relevant calcium and then magnesium. Find out what is the objective, to what level do you want to remove, is it 200, 150, 80, 40 or such, and then you will calculate the amount of lime or such required, right? How is it? You want to remove carbon dioxide in all the case. If there is any carbon dioxide, all of it will have to be removed, and then add excess dose of lime when magnesium is also being removed, so that what is it now? You have magnesium carbonate hardness being removed, right, along with the calcium carbonate hardness. And if the calculated lime dose does not exceed alkalinity plus CO2, then pH may not be high enough to drive the reactions. That is one thing to keep in mind. If I am adding lime and all the lime is consumed by the alkalinity or the CO2, it is not increasing the pH. So, that is something that you have to keep in mind. Then pH might not be high enough to drive the reactions. This is true when magnesium, I guess, carbonate hardness should be removed. In that case, lime should be increased, right? Lime dose should be increased to alkalinity plus CO2 plus excess, let us say, right. So, that is something to keep in mind. Why? As I told you, magnesium will be removed at relatively high pH, around 11.5. So, the pH has to be increased considerably. That is why you are adding this excess to. That is something to keep in mind, right. So, let us move on. Okay, so looking at this table or the summary earlier, what is it that we have here, right? We have lime dose. So, for removing 1 mole of carbon dioxide, 1 mole of calcium associated with carbon hardness, 1, and for magnesium associated with carbonate hardness, 2 moles of lime, and the one associated with non-carbonate hardness, 1 mole of lime, and some excess has to be added to drive the relevant reaction. That is something to keep in mind. What about soda ash? Okay, minimum lime dose obviously will be alkalinity and carbon dioxide, because all the OH minus you are going to add will be taken up by this CO2 or H2CO3, and alkalinity is nothing but acid neutralizing capacity. So, you have to add excess or enough to be able to remove this. This is for the minimum lime dose, and excess will have to be added, especially if magnesium has to be removed. Let us see, all the units are being expressed as CaCO3. That is something to keep in mind. What is soda ash or not what is soda ash? When is soda ash to be added? When I have no carbonate present in my solution, I have to give the relevant CO3 2 minus, and it is added when I have to remove calcium non-carbonate hardness or magnesium non-carbonate hardness, and obviously excess to drive the relevant reaction. So, obviously I see that it is 1, I guess, right, for each case. So, let us move on. So, we have one example here or a simple example here. Let us just look at that and wind up for now, and then we will have one more session probably where we will wrap up lime soda softening. So, we have it for a water sample. Here we have the data such that it is easy for us to understand whether it is carbonate hardness or non-carbonate hardness. Flow rate is 50,000 liters per day or 50 KLD. The slaked lime purity is 86%. This is something to keep in mind. Again, the purity here that is mentioned is actually pretty high. Typically, it might be around 70%. So, that is one aspect. Purity of the soda or the soda ash is Na2CO3. This typically is relatively high, 98%, and we are asked to calculate the daily requirement of lime and soda ash respectively, right. So, here we have different impurities and the relevant concentrations. So, first thing is to understand, let us say, per liter how much lime or soda ash that I need to add. Once I have that, I have the flow rate, which is volume per time, right, volume liters per day time, and then I will be able to calculate the required lime or soda ash per day. It is pretty simple. So, first approach is to look at this. So, as I can see, I have calcium here, magnesium here, magnesium here, magnesium here, right. So, and also calcium here. So, calcium is associated with carbonate hardness, calcium is also associated with non-carbonate hardness, right. They are making the job here easier for us. If not, you will have had to look at general understanding of this kind of a chart, where is this, or I guess this, and do so, let us see, right. But there we would have, let us say, if I had information like this, Ca2 plus, Mg2 plus and HCO3 minus independently, right. Rarely will we ever have it in this manner, right. We won't know in what form the CaCO or calcium came in. We do not know whether it came in from CaCO3 or other form. So, typically you will only be able to measure Ca2 plus or Mg2 plus. You can't measure CaCO3 directly, that is dissolved in the solution. Once it is dissolved, it will be present as the relevant ions, let us see. But in this example, we are taking a theoretical look. But if not, in general, what will you be able to measure? You will be able to measure calcium. So, I will write calcium here, and I will be able to measure magnesium. I will be able to write magnesium here. I will be able to write alkalinity, HCO3 minus or HCO3 minus, and then maybe the other anions, let us see. Then I will say, okay, the Ca2 plus will be due to, or I will have some calcium and carbonate hardness, and as I can see, alkalinity is less than the calcium concentration. So, I will also have calcium non-carbonate hardness, and then I will say all the magnesium will be associated with only non-carbonate hardness. That is the typical approach if the ions are given. This is the usual way, but here I guess people were just trying to throw it off scent, but you understand my issues with the questions being framed in this manner. You can't measure CaCO3 directly, but you will measure the ions. Fine, that is enough. So, what about magnesium? It is present in the form of carbonate hardness in some cases, present in the form of non-carbonate hardness in some cases. So, in a way they are making the job easier. Let us move on. So, what do we have? We have listed them out here. Equivalent weight, again equivalent weight, we are, let us say, for CaCO3, right, it is either Ca2 plus or CO3 2 minus, each one charge 2, let us say, right. So, that is why it will be molecular weight by N, and N in this case is 2, let us say, right. Same case you can look at it for all the other cases here, right. For here it is going to be 1, here it is 2, same case 2 here, 2 here, 2 here, I am talking about the valency, I guess, right, and here it is 3 plus, I think, is not it? Okay, not even 3 plus, I think it is 6 here if I am not wrong, right, because it is Fe 3 plus and I have 2 of them, so it is 6 plus here, right, and same case oxygen is 2 minus, I have 3 of them, so it is 6 here. Ca2 plus SO4 2 minus, so it's 2 here. SiO2, I guess it's going to be equal to 4 here, right. So in that manner, I guess you can get this particular setup here, not setup, equivalent weight, molecular weight by N, let's say, and you can get that particular aspect here. So based on that, you have the relevant valency, and from that you can get the relevant equivalent weight here, molecular weight by the valency, and you will calculate the equivalent weight, right. And then you will be able to calculate the equivalents per liter. How do I get that? Let's say I have the concentration here, milligrams per liter, right, and I want equivalents in the top, let's say, right. So I will have to have mass in the bottom, or per one equivalent, what is the weight, gram of that particular compound. So then grams will cancel out, I will have it in terms of equivalent. So in effect I am dividing by equivalent weight, but you know or the approach that I prefer. But again, here for putting all the data into one table, we what do we say, trimmed some of the aspects. If not, I would have written valency, molecular weight and gone from there, fine. So here I have it as equivalents, and then I know this, that for CaCO3 it is per one equivalent, it is 50 grams of CaCO3, right. This also we calculated earlier. So if I multiply it, 50 grams of CaCO3 per equivalent, then I will end up in this last column, 1, 2, 3, 4, 5, fifth column, right. So that is what I have. From these two, I will get the fourth column. Multiplying the fourth column by this, I will end up with the fifth column. So all the units are now expressed as CaCO3. Obviously, CaCO3 280 milligram per liter will be as CaCO3 itself, right. So that's something to keep in mind. So let's move on and see what else we have. So lime dose, there is no carbon dioxide present, and we already have this from earlier. For now, we are not saying that there is any excess, but in general, always keep in mind that excess has to be added. So from that, we are just calculating how much CaCO3 is required. Obviously, we need equivalents. Why is that? Because I can't compare concentration of carbon dioxide, so on and so forth here. If you want, you can calculate the concentration of lime in terms of moles and then transform it into CaCO3, but it's easier to express everything in terms of CaCO3, right. Let me move on, and then so this is the amount of lime that has to be expressed as or added as CaCO3 to remove the relevant hardness. And then okay, we want it in terms of COH twice concentration. So equivalent weight of COH twice concentration by equivalent weight of CaCO3. Then the units are going to be as milligram per liter as CaOH twice. So what is this? 37 by 50, and I guess this is the amount of CaOH twice I have to add in terms of mass of CaOH twice per volume, right. Here the units were as CaCO3, and we just transformed them into units of CaOH twice because I think the question asked for that. What about soda ash? Okay, let me finish daily lime requirement. So this is mass per volume is what I calculated, but I want daily, per time or per day, how much is required. So for that, I will have to multiply that by volume per time, let's say. So then I will get mass per time, right. So volume per time is nothing but flow rate. So you just have to change the units and such, 1 liter and such, you know the mass of water and such, you can change that, and that seems to be saying that I need 23.27 kgs of calcium hydroxide or lime per day. But one thing to note, that our source of lime is not pure, I have to add that. So 86%, so if I divide this by 0.86, this is the value that I will need. So I need 27 kgs per day of lime and not the 23 that I calculated earlier. Why? It's only 86% pure. So that's why I'm dividing it by 0.86. So same case with soda ash. I know this from the relevant setup that I have earlier, and I will plug that in. Yes. And magnesium and non-carbonate hardness, we already looked at that, so I will not go back there. So first as CaCO3, and then now I want it as Na2CO3, right? And this is what we have. Fine, this is now as Na2CO3, let's say, right? And same case as lime, here I have to calculate the dose. So here I am going to multiply that by the flow rate. So I will get it mass per time, right? And purity is 98%, so I have to divide by 0.98, yes. I'll now need to add 15, what do we say, kgs or 16 kgs per day, let's say. Keep in mind that in both these cases, we haven't looked at adding the excess, but without adding the excess, you will never have to or never be able to get that particular precipitation going. So that's something to keep in mind. If the question does not ask for excess, you can always write a rider that excess has to be added, right? So with that, I will end today's session, and we will look at different configurations and such in the next session, and probably wrap up this hardness removal by lime soda softening. And with that, thank you.